My name is Ryan Flanigan, and my partners were Matthew Behary and Jordan Loy, and our project was the Eagle Manufacturing Secondary Operation Prototype. So Eagle Manufacturing is based out of Wellsburg, West Virginia, and they specialize in high-quality industrial safety products. Our project was based on the extrusion blow molded HDPE barrels, which range from 38 liters to 208 liters. They currently use a secondary operation that is a hot knife assembly, but this limits the capabilities of the extrusion blow molder. The objective of our project was to reduce the secondary operation process cut time by 10 to 20% or 9 to 18 seconds. The key aspects of concern was the surface finish, the linearity of the cut, and the degree of material degradation. So our first method we utilized was a plasma torch, which this produced open flame and fumes during each cut, which produced charring on the surface, as well as it was impractical to cut the 3D workpiece. There was an unacceptable warpage of 86 millimeters, and there were inconsistent cuts with rounded edges. Our second method was a hot wire cutter, which produced long cut times and poor surface finish, as well as the material had the capability of welding back together to negate the cut.
Upon the failure of the plasma torch and hot wire cutters, the group decided to change focus into modifying the tooling of the mold rather than the secondary operation itself. So the group looked into using an in-mold blade insert, which was inspired by Caltech's Machinabah's design. This insert was to allow the cutting operation to remove material faster by thinning down the wall thickness at the cutting region. However, the group was not able to achieve this effect, so a redesign was conducted as to create a cutting groove for the hot knife assembly to run in rather than thinning out the wall thickness. So the addition of this cutting groove was able to reduce the cutting time from 30% up to about 66% through different trials. The group then moved forward with incorporating the geometry of this in-mold blade insert into Eagle Manufacturing's mold. So the mold was redesigned to utilize the geometry as seen in the finalized in-mold blade insert. So these modifications were only necessary to the dome segment of the mold, as Eagle uses a stacked up version of a mold rather than one solid mold itself. And this redesign can either be conducted as a permanent installation on the mold or interchangeable inserts as Eagle Manufacturing sees fit.
The bar chart in Figure 10 shows the average cut times of the bottles molded with and without the in-mold blade inserts. As can be seen in this bar chart, every iteration of cutting with the insert molded bottles was at least 33% faster than when cutting with the non-insert molded bottles. So in conclusion, the group believes that through the utilization of an in-mold blade insert, the secondary operation cut time can be reduced beyond the originally asked 20%. This in-mold blade insert establishes a cutting groove for the existing hot knife to cut within, ensuring complete linearity of the cut. It also helps to thin the cross-sectional area at the cutting groove, reducing the overall volume of material needed to be cut. And the geometry of the in-mold blade insert can be changed to account for different barrel volumes. The team would like to thank some specific people for helping us complete the project. Firstly, we'd like to thank Mr. Nicholas Vitelli for being the faculty advisor, Mr. Brian Young and Mr. Bradley Johnson for being project graders and continued support, Mr. Ethan Ravati with Eagle Manufacturing for sponsoring the project and helping us through it, Mr. David Honored for hot wire insight and assistance, Mr. Andy Bartlett and Mr. Chris Bartlett for plasma cutting assistance as well as troubleshooting, and Mr. Andrew Hobson with Caltech's Machinabah for insight on the in-mold blade insert. Thank you very much for listening to our project.